The sun is whispering at Earth right now, not shouting, not exploding. Whispering. A slow, steady leak of charged plasma pouring out of a coronal hole, compressing our magnetosphere, pushing KP to 6, tripping NOAA's alert system, and doing it quietly enough that most of the world hasn't even noticed. But while that whisper has been leaning on our magnetic shield for the last several hours, something else has been happening underground. 3 earthquakes, magnitude 5 or bigger, on 3 fault systems that share nothing in common except a planet. Same 7-hour window, different oceans, different physics, and the uncomfortable part? This isn't the first time. Every single time a storm like this one hits, the same pattern flickers into view. And every single time the same 3 quiet scientists quietly pull up a chart and ask the same question, nobody in their field is allowed to answer out loud. You need to see what they're looking at. Stick around. But before we go any further, if you genuinely enjoy what we do here at Project Nightwatch, hit like and subscribe so you do not miss how this story unfolds. Drop a comment with where you're tuning in from and tell me this. 3 unrelated faults on 3 sides of the planet cracked in 7 hours while a G2 storm was actively hammering Earth's magnetic field. Coincidence? Or a pattern nobody has put a name on yet? Tell me what you think. Now, let us get into it. The solar storm slamming Earth. Right now is hiding something nobody is talking about. Right now, as you're watching this, 3 things are happening at the exact same time, and none of them should be related. A G2 geomagnetic storm is hammering Earth's magnetosphere. A stream of charged particles is pouring through our planet's magnetic shield at roughly 600 kilometers per second. And in a 7-hour window that just closed, 3 separate earthquakes, each one above magnitude 5, fired off along 3 completely different tectonic boundaries, scattered across the Pacific, the Indian Ocean, and the top of the world. The Geomagnetic trench cracked open at magnitude 5.9. The Carlsberg Ridge shuddered at 5.5. The Aleutian snapped at 5.0. 3 faults, 3 oceans, 3 stress regimes, 0 shared geology, 1 timeline. And somewhere tonight, in 3 different universities in 3 different countries, 3 quiet scientists are pulling up the same chart they always pull up when a storm like this hits. They won't publish what they see. They won't talk about it at conferences, but they keep looking. Because every single time the KP index climbs into the red, the same uncomfortable question crawls back out of the margins of their field and refuses to go back in the box. And that question is the one nobody is allowed to answer out loud. The overlap nobody wants to lead with. Let me walk you through the timeline exactly as it unfolded, without any interpretation, without any spin, and without telling you what to feel about it. Because what you do with it afterward is your business. My job is to hand you the raw sequence. It started with a solar wind enhancement, a coronal hole on the sun, one of those dark magnetic gaps in the corona where the plasma just streams out unbroken into space, had rotated into geo-effective position. The stream hit Earth's magnetosphere and started compressing it, pushing the bow shock inward, and the KP index, which is the planet-wide pulse reading for how rattled our magnetic shield is, climbed from quiet levels into storm territory. It hit 6. That's a G2 storm on NOAA's 5-step scale. Not catastrophic, not the kind that knocks out power grids or strands satellites, but enough that the Space Weather Prediction Center fired off an ALTK06 alert, which is the automated notice that tells operators, utilities and aviation authorities that the planet is currently being worked on by the sun in a measurable way. This happened in the window we're talking about. Not last week, not last year, right now. And here's where it gets strange, because while that alert was live and the storm was still cresting, the seismographs started talking. The first event came out of the Geomagnetic trench, that long, terrifying scar in the Pacific seafloor northeast of New Zealand where the Pacific plate is diving underneath the Australian plate. Magnitude 5.9, a respectable event, deep subduction physics, the kind of quake the Geomagnetic fires off a few times a month without anyone paying attention. Then, hours later, a second event on the Carlsberg Ridge, which is a spreading centre in the middle of the Indian Ocean, where 2 plates are pulling apart rather than colliding. Magnitude 5.5. And then, closing out the window, the Aleutians lit up at magnitude 5.0, along that long chain of islands curving off the edge of Alaska. 3 events, 3 magnitudes above 5, 7 hours, 3 completely unrelated tectonic systems on 3 different sides of the planet. And through all of it, the magnetosphere was still ringing. Now, before you run off with that, you have to understand something. The Earth fires off about 1 to 2 magnitude 5 quakes on any given day, globally, on a normal baseline. That's just the planet breathing. So 3 in 7 hours is elevated, but not outrageous. It's a statistical bump, not a statistical miracle. If you ran this experiment over 1,000 days, you'd see clusters like this show up naturally, simply because earthquakes don't schedule themselves politely. They come in bursts. But here is the part that makes the whole thing refuse to sit still. Yesterday we had almost the exact same setup. Solar wind enhanced, KP climbing, alert conditions active, and the seismic record did absolutely nothing unusual. It held to baseline. No clusters, no surprises. Just the normal low hum of a restless planet. Same dataset, different story, 24 hours apart. And that is the thing that gets under your skin if you stare at this long enough. Because it means whatever you thought you saw yesterday didn't hold today, and whatever you're seeing today might not hold tomorrow. Which brings us to the question that is the spine of this entire investigation. Is the temporal clustering we are watching right now, during a live geomagnetic storm, a meaningful signal that the Sun and the Earth's crust are in some kind of conversation we haven't fully decoded? Or is it just the beautiful, maddening randomness of a complex planet, doing what complex planets do, while our pattern-hungry brains paint causality all over it? Because both answers are alive tonight, and both have consequences. The storm isn't the story until it is. You need to understand what kind of storm this actually is, because the label G2 doesn't communicate much unless you've spent time in the space weather world. And this particular flavour of storm, the coronal hole high-speed stream, is one of the most underappreciated drivers of geomagnetic activity on the planet. When most people think of a solar storm, they picture a coronal mass ejection, a CME, that's the dramatic one, the billion-ton cloud of magnetized plasma that the sun vomits out during a flare, the kind of event that gets Hollywood trailers. A CME is fast, it's violent, it's loaded with compressed magnetic field, and when it slams into Earth's magnetosphere, it does so like a truck hitting a trampoline. That's the kind of storm that takes down transformers and gives you auroras in Mexico. What we have right now is different. A coronal hole high-speed stream, or CHHSS for short, isn't an explosion. It's a leak. Coronal holes are those dark patches you see in extreme ultraviolet images of the sun, regions where the magnetic field lines are open rather than closed, which means the solar wind escapes from them without being bottled back up. The result is a continuous, steady fire hose of charged particles that moves faster than the normal background solar wind. Not a punch, a pressure wash. It doesn't rattle the magnetosphere in one dramatic shove, it leans on it for days, and that is exactly why this storm is so easy to miss. It's quiet, but effective. It doesn't generate the big headlines. NOAA flags it, aurora chasers get excited, and everyone else goes about their day. But the energy it deposits into the magnetosphere, the ionosphere, and the upper atmosphere is real, and it accumulates. KP6, moderate on paper, still represents a noticeable compression of Earth's magnetic shield, real current flows in the polar ionosphere, and measurable ground-induced currents depending on where you happen to be standing. Now here's where the timing gets interesting, because this storm is not landing on a neutral Earth. It's landing on an Earth that is right now tilted into one of the two positions in its orbit when geomagnetic coupling is at its most efficient. We are near the equinox, and near the equinoxes something called the Russell-McFerrin effect kicks in. I'll spare you the vector math, but here's the short version. The geometry between the solar magnetic field direction and Earth's magnetic dipole tilt aligns more favourably during the weeks around March and September. The result is that the same solar wind, with the same speed and the same density, produces a measurably stronger geomagnetic response during equinox windows than it does at solstice. Which means the storm itself, the thing pouring into our atmosphere right now, isn't unusually strong. But Earth's response to it, right at this moment in the orbital calendar, is amplified. The sun didn't change, our angle to it did. And that distinction matters because when people talk about correlations between solar storms and anything else, they almost always forget that the Earth is not a static target. Sometimes it flinches hard, sometimes it barely notices. Same storm, different flinch. So what we have on our hands is a predictable, well understood, meticulously measured space weather event, rolling over a planet that is currently in its most geomagnetically receptive posture, while 3 faults on 3 different sides of that planet choose, within a few hours of each other, to release accumulated strain. And that is where the predictable physics ends and the unpredictable human interpretation begins. Because the storm is real, the timing is real, the earthquakes are real, and whatever thread you want to stitch between them, real or imagined, is going to have to survive the next part of this investigation. 3 fault systems that shouldn't be talking. To understand just how strange the clustering is, or how normal, depending on which side of this argument you land on, you need to understand what we're actually looking at when we say 3 M5 plus earthquakes in 7 hours. Because these were not 3 tremors on the same fault. They weren't even 3 tremors from the same kind of fault. They were 3 completely different species of geological event, firing off on 3 completely different sides of the planet, under 3 completely different stress regimes. Let's start with the Geomagnetic. The Geomagnetic trench is part of a subduction zone, which means one tectonic plate is diving down underneath another one. Specifically, the Pacific plate is being shoved beneath the Australian plate at roughly 60 millimeters per year, which is fast as these things go. Subduction zones are where the biggest earthquakes on Earth happen. Not always, but often. They're compressional systems. The crust is getting squeezed, jammed together, forced downward, and the friction along the interface between the 2 plates builds up for years, sometimes centuries, until it breaks. When it breaks, it can release catastrophic amounts of energy. A magnitude 5.9 in the Geomagnetic is, honestly, a routine Tuesday for that fault. It fires these off regularly. Not scary in context, but real and measurable and part of the timeline. Now swing the camera 12,000 kilometers to the west, to the middle of the Indian Ocean. The Carlsberg Ridge is nothing like the Geomagnetic. The Carlsberg is a mid-ocean ridge, which means it's a spreading center. Instead of 2 plates colliding, 2 plates are pulling apart, with fresh magma welling up from below to fill the gap. It's an extensional regime. The stress direction is literally the opposite of what's happening at Geomagnetic. Earthquakes on spreading ridges tend to be smaller, shallower, and mechanically distinct from subduction quakes. They happen because the crust is being stretched, not squeezed. So when the Carlsberg fires off a magnitude 5.5, it's using an entirely different physical mechanism than the Geomagnetic did. And then we have the Aleutians. The Aleutian arc is another subduction zone, yes, similar in gross mechanics to the Geomagnetic, but it's offset by roughly 10,000 kilometers, sits at a completely different latitude, experiences a different climate, a different crustal thickness, a different sediment load, and a different seismic history. The Aleutians are one of the most seismically active regions on the planet. Frequent routine activity. A magnitude 5.0 in the Aleutians is, again, a pretty ordinary event in isolation. What I want you to sit with is this. There is no physical mechanism in any textbook, any peer-reviewed paper, or any mainstream geophysics model that allows stress from the Geomagnetic trench to influence the Carlsberg Ridge, to influence the Aleutians in real time. The seismic waves from an M5.9 do propagate around the planet, yes, but they attenuate rapidly, and by the time they reach the opposite side of the world, they are far below the energy threshold needed to trigger an independent earthquake on a completely different fault system. The 3 faults are not connected, they are not talking. They are, as far as the physics we understand is concerned, sovereign events, independent, uncorrelated, strangers to each other, and that is what makes temporal clustering across these 3 systems visually striking, even when it is statistically unremarkable. Because your brain is not a statistical processing engine. Your brain is a pattern-finding machine, shaped by evolution to notice coincidences, because in the ancestral environment, coincidences sometimes meant a predator was about to jump out of a bush. That reflex doesn't shut off when you're looking at a seismograph. When 3 fault systems with no shared geology fire off within a single news cycle, your brain goes looking for a connector, a hidden thread, a cause that ties them together. But here's the thing, earthquakes, at the global scale, behave like what physicists call a stochastic process. They're random in timing but bounded in rate. The planet fires off roughly 1 to 2 magnitude 5 events per day, averaged over long windows. That means the probability of 3 events in a 7-hour window is elevated, but not at all impossible. In fact, if you ran the experiment long enough, you'd expect such clusters to appear several times per year, simply from random variance. Which brings us back to the thread running through all of this. Is the clustering you just heard about the signature of something, or is it the mathematical ghost your brain is manufacturing because 3 unrelated fault systems happened to speak on the same day the sun was shouting? The tsunami warning that shouldn't exist. Embedded in the timeline of this event, there is one data point that makes the whole story a little weirder, and it's worth stopping on for a minute because it's the kind of thing that fuels rumour and confusion if you don't understand what's actually happening in the background of our global monitoring systems. The Aleutian event, the magnitude 5.0, triggered, at least briefly in some feed or another, a tsunami-related flag. Not a full-scale regional evacuation alert, not a screaming emergency broadcast, but a notification somewhere in the automated warning infrastructure that, if you saw it without context, might have made you think something far worse had happened. Here is the problem. A magnitude 5.0 earthquake at roughly 35 kilometers of depth in the Aleutian subduction zone should not generate a tsunami. Period. The physics don't support it. Tsunamis are generated primarily by the vertical displacement of seafloor, and vertical displacement on the scale needed to move ocean water meaningfully requires, at minimum, a magnitude in the high 6s or low 7s, usually larger, and typically at shallower depths than 35 kilometers. A magnitude 5.0 is below the threshold, way below. So when a warning adjacent flag appears in the system, it raises a very reasonable question. Why is it there? There are a few plausible explanations, and none of them involve hidden events or conspiracies. The first is that automated alerting systems sometimes fire on the first, least refined estimate of an earthquake's parameters. The initial magnitude estimate can be higher than the final, and by the time seismologists refine the solution and downgrade the event, an automated flag may already have been dispatched. That flag then gets retracted, or replaced, or simply superseded. But in the few minutes between the initial trigger and the correction, it exists in the system. The second explanation is data pipeline lag. Global seismic monitoring is a web of interconnected feeds run by multiple agencies in multiple countries using multiple algorithms. The US Geological Survey, the Pacific Tsunami Warning Center, the NOAA Tsunami Infrastructure, regional centers, National Meteorological Services, and countless third-party aggregators all pull from shared and redundant data streams. These systems don't always update in perfect synchronization. A warning flagged in one feed may persist for minutes or even an hour in a secondary feed that hasn't yet pulled the updated status. So you can end up with a situation where one dashboard says everything is fine and another dashboard says there's an active advisory, and both are technically reflecting accurate data as of the moment they last synced. The third possibility is precautionary automation. Some systems are configured to flag any event over a certain threshold in certain regions, regardless of whether a tsunami is actually likely, simply because the downside of missing a real tsunami is catastrophic, and the downside of a false flag is a few minutes of confusion. Risk management calculus baked into the software. None of these explanations are exciting. None of them involve hidden larger earthquakes, or suppressed magnitude data, or any of the dramatic narratives that fill up the comment sections whenever something like this happens. But they do matter for understanding why, during periods of heightened attention, like say a live geomagnetic storm with 3 M5+ earthquakes already on the boards, a small data inconsistency can balloon into perceived evidence of something much bigger. An anomaly in the data pipeline is not an anomaly in the Earth, it's an anomaly in how we're reading the Earth, and this is the reason I bring it up. When you're stressed, alert, and watching the world for signs, the signal and the noise become hard to separate. Every flicker in the data looks like it might mean something, and when a storm is active and earthquakes are clustering, every tsunami flag, no matter how quickly it gets retracted, adds to the sense that something larger is unfolding. That perception is doing real work in shaping how people interpret the core question, and that is what makes it worth addressing directly, rather than ignoring it, because pretending these anomalies don't exist is what creates the vacuum that bad explanations rush in to fill. The forbidden chart. Every field has the unofficial tool, the one that nobody teaches in grad school, the one that doesn't get cited in the flagship journals, the one that sits quietly in someone's bookmarks bar, waiting for the next big event to justify opening it again. In space weather and seismology, that tool is a chart, a very specific kind of overlay. It plots the KP index on one axis and global magnitude 5+ earthquake rates on the other, stacked over time, and it has existed in various forms for decades. I'm going to be careful with my language here, because there are a handful of researchers around the world who have worked on this kind of overlay seriously and professionally, and many more who have played with it in the margins of their actual published work. I don't want to sensationalize them, and I don't want to imply that they're part of some underground network of truth seekers being silenced by the establishment. The truth is a lot more human than that. They're just curious people, with the appropriate training, who notice the same thing you're noticing right now. Storms and quakes sometimes seem to line up. Sometimes they don't, and the ambiguity itself is what keeps pulling them back in. The chart, when you look at it, is not a smoking gun. That is the first thing to understand. It does not show a clean, obvious correlation. It does not reveal a hidden pattern that mainstream science is ignoring. What it shows, at best, is a faint statistical wobble, a possible tendency, a signal that emerges in some datasets and disappears in others. The signal strength depends on how you filter the data, what range of magnitude you include, whether you look at shallow or deep earthquakes, what time window you use to bin the events, whether you normalize for seasonal variation, and about a dozen other methodological choices that can make the correlation appear or vanish. This is why the chart has survived without the conclusion surviving. It is an exploratory instrument, not a predictive tool. It does not tell you that a solar storm will trigger an earthquake. It does not tell you that a quiet sun means a quiet Earth. It is, at best, a visual prompt that reminds a handful of researchers to keep asking the question, to not close the book entirely, to stay open to the possibility, however weak, that there is something in the data that the current models don't quite capture. Which brings us back to the central thread. The reason that chart exists, the reason it keeps getting opened, the reason 3 quiet scientists I'll never name by name are pulling it up right now, is the same reason you've spent this long listening to me describe 1 storm and 3 earthquakes. The weak correlations refuse to go fully away, even when they fail to reach statistical significance, even when they vanish in half the datasets, even when the energy physics says they shouldn't exist. Something about the pattern, or the perception of a pattern, keeps the question alive. And that is what we're going to dig into next, because the question is bigger than any single storm. It is built on decades of incomplete data, conflicting studies, and a quiet corner of geophysics that nobody wants to claim or fully reject. Yesterday broke the theory. Here is the part of the story that doesn't get told often enough when people breathlessly connect solar storms to earthquakes, and it's the part that has to be told if we're going to be honest with each other about what the data actually says. Yesterday. Not last year, not last decade. Yesterday. 24 hours before the 3 magnitude 5+ events I just described, we had a very similar setup. The solar wind was elevated, the KP index was climbing, the Earth was taking a hit from a stream of high-speed plasma, and the geomagnetic conditions were disturbed enough that space weather forecasters were flagging the day as active. If the simple story were true, if heightened geomagnetic activity automatically caused, or even reliably correlated with increased seismic activity, we should have seen the same kind of clustering yesterday that we're seeing today. 3 magnitude 5s, maybe more, distributed across random and unrelated fault systems, lining up within a single digit-hour window. We didn't. Yesterday, the global seismic record did what it does on a normal day. A couple of magnitude 5s scattered in time and space, no clustering, no anomalies, nothing that would make anyone look twice. The sun was acting up. The Earth was not. And that, right there, is the kind of result that science has to take seriously, even though it's way less interesting than the alternative. In physics, we have a concept called a negative result. It's when you run an experiment or observe a natural phenomenon under conditions where you would expect a certain outcome if your hypothesis were correct, and the expected outcome doesn't appear. Negative results are frankly undervalued in most sciences. They don't make headlines. They don't get featured in popular articles. They don't go viral on social media. But they are absolutely essential to honest inquiry, because a hypothesis that cannot be falsified is not a hypothesis, it's a belief. Yesterday's non-event is a negative result. It tells us that the causal story, the clean, simple version where solar storms drive earthquake clustering, cannot be the whole picture. If it were, yesterday should have looked like today. It didn't. So either the correlation is weaker and more conditional than a simple causal story would suggest, or the correlation is essentially zero, and what we're seeing today is coincidence. or there's some additional variable, something we're not measuring, that modulates whether a given storm produces a clustering day or a null day. Any one of those possibilities is defensible. None of them is the cinematic version. This is where the replication problem in space weather correlation studies becomes unavoidable. Replication means that if an effect is real, you should be able to see it over and over again under similar conditions. It doesn't mean the effect has to appear every single time, because real-world systems have noise. But the effect should appear often enough and reliably enough that the statistical signal emerges from the noise. In the literature on solar activity and earthquakes, replication has been a persistent problem. One study finds a weak positive correlation, another finds none, a third finds a correlation only in certain subsets of the data, and the next study contradicts the third. The pattern across the body of work looks exactly like what you would expect from a null hypothesis dressed up in statistical flukes, or from a real but very weak signal hiding in a very noisy system. Both look the same from the outside, and that is why the question keeps surviving. Not because the evidence is compelling, because the evidence is inconclusive. And inconclusive is the worst place for a scientific question to be stuck, because it neither confirms nor refutes, it just lingers. And every time a day like today shows up, the question resurfaces. Every time a day like yesterday shows up, it recedes, and the seesaw keeps seesawing, which is why, if you're going to think seriously about the central thread tonight, the question of whether the solar storm and these 3 earthquakes are connected, you have to hold in your mind not just the clustering we're seeing now, but the absence of clustering we saw yesterday. Both data points are part of the dataset. You don't get to pick one. Why today should also be nothing? Let me give you the statistical picture that every geophysicist has in the back of their head when they look at a day like today, because it's the context that reframes what we're actually seeing. Globally, the Earth produces somewhere between 1 and 2 magnitude 5+ earthquakes per day on average. That's the baseline. It's the background hum of a planet whose interior is cooling, whose plates are grinding, and whose crust is constantly releasing the stress that accumulates along its boundaries. Now, 1 to 2 per day is an average. Averages hide a lot of variation. The actual distribution of events in time follows something close to a Poisson process, which is a mathematical model that describes events happening randomly at a constant average rate. In a Poisson process, events don't arrive evenly spaced out, they clump. That's not a bug of the model, it's a feature of it. If I tell you the average is 1.5 events per day, that doesn't mean you'll see 1.5 events every day. On some days you'll see 0, on other days you'll see 3 or 4. The clumping is intrinsic to the randomness. It doesn't require a cause, it emerges from the math. So what's the probability of seeing 3 magnitude 5+ events in a 7-hour window, given a baseline of roughly 1 to 2 per day? It's not vanishingly small. It's not every day either. It's the kind of event you would expect to see multiple times per month, purely from random variance. If you sat down with a calendar of the past year's seismic activity, you would find plenty of windows of that length containing 3 or more events, and plenty containing 0, and plenty containing 1 or 2. The distribution is not smooth, it's bumpy. And the bumps are not evidence of anything other than the fact that random processes are bumpy. This is one of the oldest and most persistent sources of confusion in interpreting data. We call it the clustering illusion. Humans are hardwired to perceive clusters as meaningful. We are pattern completers. When we see 3 things happen close together in time, our brains almost automatically generate a narrative to explain why they happen together. And that narrative feels intuitive and compelling, because narratives are how we make sense of the world. But the narrative is generated post hoc after the fact, based on the assumption that a cluster implies a cause. The assumption is wrong. Clusters appear in random data all the time, not because there's a cause, because randomness produces clusters. If you could visualize the expected variance bands around the global earthquake rate, you'd see them as fat envelopes, not thin lines. A day with 3 magnitude 5s sits comfortably inside the normal variance envelope. A day with 0 magnitude 5s also sits comfortably inside it. A day with 7 magnitude 5s would be unusual but not impossible. The envelope is generous, because random processes are generous with their variance. There's a companion concept worth introducing here, which is the difference between rarity and salience. Rarity is a statistical property. How often does an event occur over a long time window? Salience is a psychological property. How much does an event capture your attention? The two are not the same thing. An event can be common but highly salient if it happens at a moment when you're paying attention and the context makes it feel meaningful. An event can be rare but low salience if it happens in the background while you're thinking about something else. Today, a G2 storm is actively happening. The news is covering it, alerts are firing, and people are primed to notice other unusual things. The 3 earthquakes are more salient than they would be on a day when nothing else was happening. But their salience doesn't change their statistical frequency. They're exactly as common today as they were yesterday. Our attention is different. The math isn't. Which circles us right back to the central thread. If the clustering we're watching is statistically within the normal variance band of a random process, then invoking the solar storm as a cause is unnecessary to explain what we see. And in science, unnecessary causes are supposed to be trimmed away by Occam's razor. Simpler explanations that don't require new physics win by default, unless the evidence forces us to reach for something more elaborate. The question is whether the evidence is forcing it. Tonight, on this dataset, looking at these numbers, the honest answer is that it is not, yet. The numbers that keep it alive. So if the clustering we're seeing today is statistically unremarkable, and yesterday's null result contradicts the simple causal story, why does the question persist? Why do serious researchers keep poking at it? Why does the literature on solar seismic correlations keep getting published? And why do new papers keep emerging even as older papers get challenged and sometimes retracted? The answer is that the data is not uniformly null. There are pockets of statistical signal, weak but not zero, that keep appearing in certain subsets of the global record, and those pockets are enough to keep the field from dismissing the question outright. Let me give you a tour of the key research lineage because it matters for understanding where the question stands tonight. In the Soviet and post-Soviet period, a scientist named Oleg Duma and various collaborators spent considerable effort looking at the relationship between geomagnetic activity and earthquake statistics. Their work, and similar work by other Eastern European researchers, suggested that under certain conditions in certain data ranges there appeared to be modest positive correlations between geomagnetic indices and subsequent seismic activity. The correlations were never large. They never explained the majority of seismic variance, but they were not nothing, and they survived enough statistical scrutiny to make it into the peer-reviewed literature. More recently, in 2020, a group of researchers led by Marchitelli published a paper that looked at global earthquake data in relation to solar wind and geomagnetic parameters, and found what they described as a statistically significant correlation between high-energy solar wind events and increased earthquake rates, particularly for shallow seismicity. The paper generated attention, both positive and critical, and it remains a reference point for anyone looking at this question seriously. It has not been definitively overturned, but it also has not been definitively replicated by independent groups using different data sets and methodologies. The conclusion is alive, but unsettled. Here's where it gets interesting. When you look carefully at studies that do find correlations, a pattern emerges. The correlations tend to be stronger for shallow earthquakes than for deep ones. They tend to be more robust for certain magnitude ranges. They tend to be stronger during certain phases of the solar cycle. And they tend to be more visible when specific geomagnetic indices are used rather than others. In other words, the signal, if it exists at all, is dataset sensitive. How you cut the numbers changes what you find. That dataset sensitivity is a red flag in statistics. It's called the Garden of Forking Paths problem. If you have a dataset large enough, and you try enough different ways of slicing and analysing it, you will almost inevitably find some slice that produces a statistically significant result, purely by chance. Unless your analytical choices are pre-registered, made in advance before you look at the data, the apparent significance of your findings can be an artifact of the many implicit decisions you made along the way. This doesn't mean every solar seismic correlation study is wrong. It means that distinguishing a real weak signal from a statistical artifact is very hard in this kind of analysis. Then there's publication bias, which is the tendency for positive results to get published and null results to get quietly filed away. If 10 research groups run the same analysis and one finds a correlation while 9 find nothing, the one paper that got published is the one that gets cited, and the 9 null results vanish into the file drawer graveyard. Over time, the published literature looks like it supports the correlation, even though the full body of work, including the unpublished studies, might not. Publication bias is a well-documented problem across all of science, and it's particularly relevant for fringe-adjacent hypotheses like solar seismic coupling, because positive results are more interesting and more publishable. But here's the thing, even accounting for dataset sensitivity and publication bias, the weak signals don't fully go away. They show up in different datasets, analysed by different groups, using different methodologies. Not every time, not with any consistency you could build a prediction on, but often enough that the null hypothesis can't quite get the coffin lid shut. The field is stuck in an uncomfortable middle zone where the evidence is too weak to confirm a real effect and too persistent to fully dismiss it. Which is why I said earlier that the signal depends on how you look. And that is exactly the question the three quiet scientists ask every time a storm like today's hits. They're not looking for a smoking gun. They're looking for one more data point in a picture that has been building slowly for decades and that still hasn't resolved. The central thread running through this whole investigation is not whether today's clustering proves causation. It's whether today's clustering, added to all the other ambiguous data, keeps the hypothesis alive or starts to tilt it toward retirement. On today's evidence alone, it tilts toward neither. It just adds one more ambiguous brick to an ambiguous wall. The energy problem nobody gets past. Now we have to confront the biggest obstacle to any causal link between solar storms and earthquakes, and it's one that even the researchers who take the hypothesis most seriously have to reckon with. It's the energy problem. And it is a wall that almost nobody gets past. The energy scales involved in solar storms and earthquakes are wildly, almost absurdly mismatched. When a G2 geomagnetic storm hits Earth, the total energy dumped into the magnetosphere and upper atmosphere is measured in the range of roughly 10 to the power of 15 joules over the duration of the storm. That is a lot of energy, in human terms. It's enough to warm up the thermosphere measurably, drive auroral currents, and cause the kind of secondary effects we actually observe, like power grid fluctuations and GPS errors. Now let's compare that to an earthquake. A single magnitude 6 earthquake releases roughly 6 times 10 to the 13 joules. A magnitude 7 releases about 2 times 10 to the 15 joules. A magnitude 8 releases around 6 times 10 to the 16 joules, and those are just the seismic radiation components. The total energy released, including heat and other forms, is even larger. The strain energy stored in a major fault zone, accumulated over decades or centuries, dwarfs the kinetic energy release of a single event by orders of magnitude. So here's the problem. Even if every single joule of energy from a geomagnetic storm were perfectly transferred into the Earth's crust and concentrated at the location of a fault, which is not physically possible by any known mechanism, the storm's total energy is not obviously greater than the energy involved in a single significant earthquake, and the transfer efficiency from magnetosphere to crust is not 100%. It is staggeringly less than that. The vast majority of the storm's energy stays in the ionosphere, gets radiated back into space, or is dissipated as heat in the thermosphere. Only a tiny fraction reaches the ground at all, in the form of induced currents, and those currents are concentrated at high latitudes, not evenly distributed across the planet. The metaphor I like, because it captures the scale mismatch pretty well, is this. Imagine you're trying to move a mountain by whispering at it. The whisper has energy. Sound is energy. If you whisper long enough, maybe the cumulative energy, over geological time, adds up to something measurable. But the mountain is a mountain. It doesn't care about your whisper in the way that, say, another mountain would. The scale mismatch between the input and the thing you're trying to move is so enormous that direct causation is physically implausible, and there's another layer on top of that, which is the shielding and damping effect of the Earth's crust and upper mantle. Electromagnetic fields from space weather penetrate only a limited depth into the ground before they are attenuated. The induced currents flow primarily near the surface. They don't reach the depths where most significant earthquakes originate, which is typically between 10 and 60 kilometers, for the events we call crustal, and even deeper for subduction events. The faults that actually break are far below the zone where space weather has any meaningful direct influence. Which means the energy mismatch isn't just about total magnitude, it's about delivery. The storm can't even get its energy to the right place. This is why mainstream seismology has historically rejected the direct causal hypothesis. The physics doesn't support it. A solar storm does not have the energy, or the coupling mechanism, or the penetration depth to directly cause an earthquake that wasn't going to happen anyway. No peer-reviewed paper has yet produced a physical model in which the math works out without invoking new and unproven mechanisms. The hypothesis, in its strong form, runs into a wall that it has not yet climbed. There's no reproducible laboratory analogue that shows solar-scale electromagnetic perturbations triggering rock fracture under crustal pressure and temperature conditions. Lab experiments on piezoelectric effects in quartz, on electrokinetic flow in porous rock, on magnetic field influences on fault friction, have produced interesting but small-scale results that don't obviously scale up to the crustal level. We haven't built the bridge from what happens in a lab bench to what happens on a fault system hundreds of kilometres long, and this is where the central thread gets sharpened into something uncomfortable. If the energy physics doesn't support a direct causal link, then the clustering we're seeing today, however striking, cannot be attributed to the solar storm in any mechanistic way that current science endorses. The storm is not a cause, not by any known mechanism, which either means the clustering is coincidence, which is the simplest explanation, or it means there's a mechanism we haven't yet discovered, some subtle pathway by which small inputs produce large effects under the right conditions. And that is the loophole we have to talk about next, because it is the one place where the hypothesis still has some room to breathe. The one loophole nobody can close. There is exactly one conceptual framework in which a solar storm could plausibly be connected to earthquake timing without violating the energy problem we just walked through. And it's worth understanding carefully because it's the framework that keeps the hypothesis alive in the minds of the researchers who haven't quite let it go. The idea is called triggering, and it is distinct from causation. If you cause an earthquake, you supply the energy that breaks the fault. If you trigger an earthquake, you don't supply the energy at all. You just nudge a system that was already about to break into breaking now, rather than 5 minutes from now or 5 days from now, or 5 years from now. The energy for the earthquake comes from the accumulated tectonic strain that was already stored in the fault. All you need to do is be the thing that tips the last grain of sand onto the pile. This is the avalanche analogy, and it's useful because it captures the physics of what's called a critical state system. Picture a snow-covered mountainside that is loaded with snow right up to its angle of repose, which is the maximum steepness at which the snowpack can hold itself together. Any additional weight or vibration or gust of wind can tip it into collapse. When the avalanche comes, the energy that drives it down the mountain is the gravitational potential energy that was already stored in the snowpack. The trigger might be a single snowflake. The snowflake has almost no energy. But the snowflake chose the moment. It didn't cause the avalanche. The avalanche was going to happen. The snowflake just picked the timing. Faults near their failure threshold, faults that have been loading stress for decades or centuries and are approaching the breaking point, might behave similarly. The breaking is inevitable. The strain is stored. What you need for the break to happen now rather than later is a small perturbation at just the right moment. And the perturbation doesn't need to be big, because the energy to complete the break is already stored in the fault itself. If you accept this framework, then the energy problem dissolves. The storm doesn't have to supply the energy to break the fault. It only has to supply a tiny push at a moment when the fault is sitting on the knife edge of failure. An electromagnetic induction, ionospheric current variations, tiny pressure changes, tiny shifts in groundwater behaviour in fault zones, tiny alterations in frictional conditions along the fault interface. Any of these small effects, if they arrive at the right microsecond, could in principle tip a fault that was already on the edge. This is why the hypothesis has not been completely killed off. The triggering mechanism doesn't require new physics. It doesn't require the storm to supply earthquake-scale energies. It only requires faults to be in a state of near failure, which some are, and a small perturbation to matter at that critical moment, which is at least thinkable. But here's the catch, and it's a big one. We cannot currently measure, with any precision, which faults are in the near-failure state at any given moment. We have models of stress accumulation, we have estimates of fault loading, we have historical seismic records that tell us where the stress is probably building. What we don't have is the ability to say, in real time, that this particular segment of the Geomagnetic trench is sitting at 99.9% of its failure threshold tonight. Without that precision, We can't test the triggering hypothesis in any rigorous way. We can't predict which faults should respond to solar perturbations. We can't confirm after the fact whether a fault that broke during a storm was actually in the near-failure state at the moment of breaking. The hypothesis is theoretically open, but it's operationally stuck. We can't design an experiment to confirm or refute it, and this is the one loophole that keeps the question alive, and you should understand it clearly. The solar storm didn't cause today's 3 magnitude 5 earthquakes. Nothing in the physics we understand allows that. What we cannot rule out, because we lack the measurement precision, is whether the solar storm nudged the timing of one or more faults that were already going to break soon. That's a much weaker claim. It's also a much harder claim to test, and that combination, weak and hard to test, is exactly the kind of claim that persists in the margins of a field for decades without being resolved. Possibility is not evidence. I want to say that plainly. The triggering hypothesis is possible. It is not supported by strong evidence. It is supported by the logical space it occupies, the fact that the energy problem doesn't kill it in the way it kills the direct causation hypothesis. But possibility alone is not proof, and if the 3 earthquakes today were genuinely triggered by the storm, we have no way of showing it was so. They look exactly like 3 random earthquakes that happened in a random window. The triggering claim cannot be distinguished, with our current tools, from coincidence, and that is the core of the problem that has kept this question open for half a century. So when we return to the central thread, we find ourselves in a strange place. The clustering today is real. The storm is real. The statistical baseline explains the clustering without needing the storm. The energy physics rules out direct causation. The triggering hypothesis leaves a thin door open that we can't walk through with current tools, and that thin door is why the question survives, and why it is about to take us into the mechanisms that get whispered about in the margins of the field, the ones that nobody likes talking about in public, but that keep getting rediscovered every time a storm like tonight's arrives. The solar seismic coupling hypothesis. Now we step into the territory that mainstream geophysics treats the way a well-run household treats an eccentric uncle at Thanksgiving. He gets a seat at the table, nobody outright rejects him, but nobody makes prolonged eye contact either. The solar seismic coupling hypothesis is that uncle. It has been around for a long time, it keeps showing up at family events, and most members of the family privately hope he'll just quietly finish his food and go home without starting a conversation. The hypothesis, in its most neutral form, is this. There exists some physical pathway by which activity at the Sun, delivered to Earth through the solar wind and its interaction with our magnetosphere, can influence the timing or occurrence of earthquakes on Earth's surface. That's it. No mechanism specified, no magnitude of effect implied. Just the claim that the pathway exists in some form, somewhere in the complex Earth system. The hypothesis emerged in modern form in the middle of the 20th century, when scientists first began to systematically measure and track both solar activity and global seismicity with enough precision to compare them. Early attempts to find correlations were, predictably, a mess. The data was sparse, the indices were crude, and the statistical methods were less sophisticated than what we have today. Some researchers reported weak correlations, others reported nothing. The conversation was happening at the margins of both fields, because space weather and seismology were themselves relatively young disciplines. Over the decades, the hypothesis has cycled in and out of visibility. It has a few different flavours, depending on which proposed mechanism you're willing to entertain. The 3 broad categories are electromagnetic coupling, where solar-driven changes in Earth's electromagnetic environment directly perturb stress in fault zones, stress modulation, where small changes in Earth's rotation rate or atmospheric pressure, both of which can be influenced by solar activity, indirectly load and unload faults, and ionospheric induction, where electrical currents flowing in the ionosphere during storms drive corresponding currents in the ground that interact with conductive structures in the crust. None of these mechanisms has been definitively confirmed. None of them has been definitively refuted either. They all sit in a kind of theoretical purgatory, proposed, partially tested, inconclusively evaluated and periodically revisited. The field hasn't closed the question, but it also hasn't committed resources to answering it in a way that would produce a definitive resolution. There are no dedicated satellite missions to investigate solar seismic coupling. There are no major government research initiatives funding it. the work that does happen is mostly done by individual researchers or small groups, often on the side of their main research programs, often with limited data and even more limited statistical power. Why isn't this mainstream? A few reasons. The energy problem, which we already discussed, creates a high bar for any proposed mechanism. The null results in many studies create skepticism about whether there's anything to find. The risk of career stigma for being associated with what looks superficially like fringe research creates disincentives for early career researchers to enter the field. And the methodological difficulty of disentangling weak signals from noise in a system as complex as global seismicity means that even dedicated work can produce ambiguous results that don't move the field forward. Why isn't it fully dismissed? Because the null hypothesis has not been comprehensively demonstrated either. The weak correlations keep showing up in enough studies to prevent full closure. The triggering loophole remains theoretically open, and in a complex Earth system with many known couplings between the atmosphere, hydrosphere and lithosphere, adding another weak coupling is not by itself outrageous. The Earth is a connected system. Things that look unrelated often turn out to be weakly coupled in ways we didn't anticipate. The falsifiability challenge is real. To falsify the hypothesis rigorously, you would need to demonstrate that no mechanism of any kind at any scale connects solar activity to earthquake timing. That's an extraordinarily broad claim to prove. It's easier to demonstrate a specific positive mechanism than to rule out all possible mechanisms, which means the hypothesis in its weakest form is nearly unfalsifiable, and unfalsifiable hypotheses tend to drift into the same grey zone as philosophical conjectures. They survive, but they don't advance. So where does this leave us on the central thread? The solar seismic coupling hypothesis is the overarching theoretical frame within which tonight's clustering of 3 earthquakes during a geomagnetic storm either matters or doesn't. If the hypothesis is wrong, tonight's clustering is coincidence. If some version of the hypothesis is right, tonight's clustering might be a small data point in support of it, but not a definitive one. The hypothesis is the reason the question persists. It's not the answer. It's the scaffolding the question hangs from. Geoelectric currents in the crust. One of the specific mechanisms proposed under the broader hypothesis involves geoelectric currents, and this is worth spending a few minutes on because it's the mechanism with the most experimental support, even though that support is still weak. Here is how it works. When the solar wind hits Earth's magnetosphere, it drives currents in the ionosphere, particularly in a region called the auroral electrojet, which is a band of electrical current flowing at high latitudes during geomagnetic storms. These ionospheric currents induce through electromagnetic induction corresponding currents in the ground below them. The ground currents, called geomagnetically induced currents or GIC, are real and measurable. They are the same currents that, in extreme storms, can overload power grid transformers and cause blackouts. They are not hypothetical, they are observed. The question becomes, what do these ground currents do once they're flowing in the crust? The crust is not a uniform conductor. Different rock types have different electrical conductivities. Sedimentary rocks tend to conduct differently than the igneous rocks. Water-saturated rocks conduct very differently from dry rocks. Fault zones, which often contain crushed rock and fluids, have conductivity properties that can differ sharply from the surrounding crust. This means the currents don't flow uniformly. They concentrate in certain regions and avoid others, following the path of least electrical resistance. In principle, if ground currents concentrate along a fault zone, and if the fault zone is near failure, the currents could interact with the stress state of the fault in some small way. They might modify the local friction, they might alter the pore pressure of fluids in the fault, they might induce small thermal changes through resistive heating. Any of these effects, if they happen at the right moment in the right place, could theoretically nudge the fault's timing. Here's the connection to tonight's clustering. If geoelectric currents were the mechanism, we would expect the effects to be strongest at high latitudes, where the auroral electrojet is most active, and in regions with specific conductivity contrast between the fault zone and the surrounding crust. The Aleutian event tonight is at a moderately high latitude. The Kermadec and Carlsberg events are at mid and low latitudes, where the direct ionospheric coupling is weaker. If the coupling mechanism is ionospheric, the Aleutian event is the most plausible candidate for any storm-related influence. The other two are much harder to explain through this pathway. The uncertainty in our spatial resolution of ground conductivity is enormous. We have magnetotelluric surveys that map crustal conductivity in some regions, but global coverage is spotty. We don't have a complete three-dimensional map of Earth's crustal electrical properties. So even if the mechanism is real, we can't predict which faults would be most susceptible to it, and we can't confirm after the fact which events were influenced. The mechanism is theoretically plausible, it is operationally invisible, and this is how geoelectric currents fit into the central thread. They are one of the proposed bridges between a solar storm and an earthquake. The bridge exists, at least in the sense that the currents are real, and they do flow through the crust during storms. Whether they can actually move the needle on fault timing is unproven. Tonight's clustering, particularly the Eleusian event, is the kind of data point that gets filed away in the back of a researcher's mind as potentially relevant, but not as evidence. It's a possible, not a probable. Quartz, pressure, and piezoelectric effects. A second proposed mechanism is more exotic and has a more checkered scientific history, and it involves the piezoelectric properties of certain minerals, especially quartz. Piezoelectricity is a property of certain crystalline materials, including quartz, in which mechanical stress produces an electrical voltage, and conversely, an electrical field produces mechanical strain. It's a real and well-understood phenomenon at the laboratory scale. You have piezoelectric crystals in your watches, in your lighters, in a wide range of industrial sensors. The physics is solid at the small scale. The proposed extension to seismology is that large amounts of quartz in the crust, particularly in stressed fault zones, could convert some of the accumulated stress into electrical signals before an earthquake. These signals might be detectable as precursor electromagnetic emissions, and in principle, they might also be influenced by external electromagnetic fields from solar storms, potentially affecting the microfracture process that leads up to a major slip event. Where this mechanism runs into trouble is scaling. A quartz crystal in a lab is a coherent, uniform single crystal object. A fault zone is a chaotic mess of rock, minerals, fluids, and fractures, with grains oriented in essentially random directions. When you apply stress to a coherent quartz crystal, the voltages produced by each molecule add up coherently, because they all point the same way. When you apply stress to a chaotic mess of rock, the voltages produced by differently oriented grains largely cancel each other out. The bulk piezoelectric effect at the scale of a fault zone is expected to be orders of magnitude smaller than the sum of the microscopic effects. There is some experimental work suggesting that under the right conditions, some coherent piezoelectric signal can emerge from stressed rock, particularly during the microfracture phase that precedes major failure. But the experimental support is limited, the effects are small, and the connection to solar storm perturbations is tenuous at best. Solar storm electromagnetic fields are extremely weak compared to the fields needed to meaningfully influence piezoelectric processes in rock. The scale mismatch we saw in the energy problem returns here in a different form. This is why the piezoelectric mechanism sits in fringe territory. It has a real scientific kernel in the form of verifiable laboratory piezoelectricity, but the extension to seismic scale phenomena, and especially to solar-triggered effects, is speculative. It keeps getting proposed because the underlying physics is real at small scales. It keeps getting marginalized because the scaling arguments haven't been worked out convincingly. Its place in the central thread is as one of several proposed micromechanisms that might, under the right conditions, contribute to solar earthquake coupling. Tonight's three events do not confirm it. They don't refute it either. They are just more data points in an ongoing conversation about whether microscale phenomena can have macroscale consequences in the Earth system. Fluid pressure and electrokinetics. A third proposed mechanism involves the interaction between fluids in fault zones and electromagnetic fields, and it's one that might have the most physical plausibility of the three we're walking through, though it's also poorly constrained by observation. Faults are not dry interfaces. Most active faults contain significant amounts of water in the form of pore fluids that circulate through fractures, pores, and permeable zones. The fluids play a critical role in fault mechanics. They affect the friction along the fault, they modify the effective stress, and they can dramatically influence when and how a fault slips. The classic example is induced seismicity from wastewater injection in oil and gas operations, where pumping fluids into the ground has been definitively shown to trigger earthquakes by changing pore pressure on nearby faults. Fluid pressure matters. Now, electrokinetics is the phenomenon by which electrical fields can drive fluid flow through porous materials, or conversely, by which fluid flow can generate electrical signals. It's another real laboratory phenomenon with a solid theoretical basis. In a fault zone, with fluids flowing through porous rock in the presence of ground currents induced by a solar storm, there is, in principle, a mechanism by which the storm could influence fluid behavior in the fault, and the fluid behavior could influence fault stability. The problem, once again, is one of scale and uncertainty. We can't directly observe fluid behavior at the depths where earthquakes occur. Most of our knowledge of fault zone hydrology comes from inference, from borehole studies at shallow depths, and from theoretical modelling. The spatial resolution we have on subsurface fluid systems is very limited, and the scale of the effects produced by solar-induced currents is expected to be small compared to the natural variability of fluid pressure in fault zones. The mechanism is testable in principle, but the test is extraordinarily difficult to design. You would need to observe fluid pressure changes in deep fault zones during solar storms, at high time resolution, with enough spatial coverage to compare storm periods with quiet periods. We don't have that capability. Borehole pressure sensors are deployed in a handful of locations worldwide. They would give us only a sparse sample of what is happening. This is speculative territory, and that's the honest framing. The mechanism is theoretically plausible. The evidence for it is weak. The tools to test it comprehensively don't exist yet. It's a hypothesis in waiting, essentially, held in reserve until we have the instrumentation to evaluate it seriously. Its relevance to the central thread is as another possible bridge. Fluid electrokinetics joins geoelectric currents and piezoelectricity on the list of mechanisms that could, in principle, link today's solar storm to today's earthquake clustering. Each of them is weak. None of them alone is compelling, but in combination, as a family of small effects that might all contribute something, they represent the theoretical space in which the hypothesis continues to live. The variable nobody tracks properly. Here's something that doesn't get talked about enough, and it's important for understanding why the question keeps coming back, even when the data looks null. The KP index, which is the main metric we use to characterize geomagnetic activity, is a coarse, planet-wide 3-hour average number. It's useful, it's widely understood, it's what goes in the news headlines. But it is absolutely not the full picture of what a geomagnetic storm actually does to Earth's surface. What the KP index misses is the rapid, localized variation in the magnetic field. The time derivative of the magnetic field, usually written as dB by dt, is what actually drives induced currents in the ground. And decibels by decibel per second can spike dramatically during brief episodes within a storm, even when the overall KP value is moderate. These spikes are localized. They can be intense in one region and barely detectable a few hundred kilometers away. They depend on the specific geometry of the ionospheric currents and the conductivity structure of the ground below. What this means is that the KP index by itself is a bad proxy for whether a given fault experienced a meaningful perturbation during a storm. Two faults on opposite sides of the planet might experience radically different decibels by seconds, environments during the same KP6 storm. One might see strong local spikes, the other might see almost nothing. If the triggering mechanism depends on rapid electromagnetic variations rather than on sustained moderate activity, then studies that correlate earthquake rates with KP will miss the real signal, because KP isn't measuring the right thing. We don't have a dense, global, real-time grid of high-time resolution magnetic field measurements on the ground. We have some, but coverage is uneven. Europe has better coverage than the Indian Ocean. North America has better coverage than the South Pacific. Mid-latitude regions are better instrumented than polar or equatorial regions. Any statistical analysis of solar seismic correlations using global KP data is, in effect, assuming that the local magnetic environment is well represented by a planetary average, and that assumption is almost certainly wrong for fine-grained analysis. This is a research gap. It's not conspiracy, it's not suppression. It's just that building and maintaining a dense global magnetometer network is expensive and not clearly justified by the benefits it would provide to most applications. Power grid operators have decent regional networks. Space weather forecasters have adequate planetary scale networks. But the network needed to rigorously test solar seismic coupling with high spatial and temporal resolution doesn't really exist. which means any conclusion drawn from current data, whether positive or negative, is limited by the resolution of the data itself. If there is a real coupling mechanism, it might be invisible to KP-based analyses because KP averages away the localized spikes that actually matter. If there isn't a coupling, KP-based analyses will correctly show no correlation, but they won't rule out the possibility that a better resolved analysis might show something. Either way, we're stuck with ambiguity. This loops right back to the central thread. The reason the question keeps resurfacing is not that the evidence is strong, it's that the evidence is limited by the tools we have. We might be looking at the right place with the wrong glasses. And until the glasses improve, the question will keep resurfacing, storm after storm, cluster after cluster, without ever being definitively answered. Tonight's 3 earthquakes are one more data point in that ambiguous picture, visible mostly because a storm is making everyone look. Why storms always seem to line up. Let's zoom out for a moment, because I want to address something that comes up constantly in conversations about solar activity and Earth events, and it's the reason why, if you watch these correlations carefully over time, you will keep getting the feeling that storms always seem to line up with something. The Sun goes through an 11-year cycle of activity. During the active phases of that cycle, geomagnetic storms are much more common, sometimes happening every few days. During the quiet phases, they can go weeks or months without a significant storm. We are currently in a relatively active phase of the cycle, which means storms are frequent. At the same time, Earth's baseline earthquake rate is approximately constant, 1 to 2 magnitude 5s per day, on average, regardless of what the Sun is doing. The two processes, solar activity and global seismicity, run on different timescales and with different drivers. They are independent, but here's what happens when you overlap them in time. If storms are happening every few days and earthquakes are happening 1 to 2 times per day, then any storm you pick will have earthquakes happening near it in time. Some of those earthquakes will fall within hours of the storm's peak. Some will fall within a day. Some will fall within a week. If you're willing to flex your definition of near in time, you can always find earthquakes that line up with any given storm. The overlap is not evidence of causation. It is the inevitable consequence of two frequent processes running in parallel. You cannot not have overlap. This is the statistical convergence problem. When two independent processes are each reasonably common, their temporal overlap is guaranteed. The question is whether the overlap is greater than expected by chance, which requires careful statistical analysis with proper null models, and the human brain is not good at intuiting what chance-level overlap looks like. We tend to see the overlaps and feel that they mean something, because each individual overlap seems striking, even when the overall frequency of overlap is exactly what you'd expect from randomness. On top of that, there's an attention bias during alert periods. When NOAA fires off a storm alert, media attention increases, people start watching for unusual events, and the salience of any coincidental occurrence is magnified. You noticed the 3 earthquakes today because you're already watching. You didn't notice the 5 earthquakes yesterday, which happened during a slightly less active geomagnetic day, because nobody was telling you to look. Attention itself is shaping the perception of the pattern. The media amplification effect makes this worse. Earthquakes are always happening, but earthquakes during a solar storm generate content. Content generates clicks. Clicks generate more content. Before long, the perception of a pattern is reinforced by the ecosystem of coverage surrounding it, even though the underlying frequency of the pattern has not changed at all. The feedback loop is social, not geophysical. So when we circle back to the central thread, we find that the clustering perception tonight is being shaped by at least 3 forces. The actual statistics of 2 independent processes overlapping, the attentional bias created by the active storm alert, and the media amplification of any coincidental occurrence. All 3 forces push in the same direction, making the clustering feel more meaningful than the raw numbers would suggest. The signal we think we see is partly in the data and partly in us. Distinguishing the two is one of the hardest problems in this whole investigation. The equinox bias. There is another layer of bias in how we perceive solar earthquake correlations, and it has to do with the time of year. Tonight we are near the spring equinox in the northern hemisphere, or the autumn equinox in the southern hemisphere, depending on which side of the planet you're on. And equinox timing matters, both physically and statistically. Physically, as I mentioned earlier, the Russell-McFerran effect enhances geomagnetic coupling efficiency during the weeks around equinox. The same solar wind conditions produce stronger geomagnetic responses during these windows than they do at solstice. This is a real, measured, well-documented effect. It means that April and October, and late March and late September, are structurally noisier geomagnetically than other times of year. More storms get to KP6 or above during these windows, even when the solar activity is otherwise comparable. Statistically, this creates a bias in correlation studies. If you look at solar seismic correlations using global data, and if some of the apparent correlations cluster around equinox periods, it's not necessarily because solar activity is driving earthquake activity more strongly during those periods. It could be because there are simply more storms during those periods, which means more overlap with the constant background earthquake rate, which means more apparent correlations. The equinox is enhancing the numerator and leaving the denominator alone. The ratio goes up. The interpretation of that ratio gets tricky. Researchers who look at this question seriously are aware of the equinox effect and try to control for it in their analyses. But control is imperfect. The effect is not purely geometric. It interacts with other variables, including the specific phase of the solar cycle, the recent history of activity, and the configuration of coronal holes on the sun's surface. Isolating the equinox bias from the potential real signal is not trivial. This is also why April is structurally noisy. We're in it right now. This period historically has produced more notable storms than an average month of the year. It has also produced more apparent correlations in studies that don't rigorously control for seasonal effects. The window we are currently in is, in a sense, the worst possible time to try to make inferences about solar seismic coupling from a single day's data, because the bias toward apparent correlation is maximized. Historical observation cycles reinforce this. Researchers going back decades have noticed that interesting correlations seem to appear more often in equinox windows than in solstice windows. Some have interpreted this as evidence for the hypothesis, on the grounds that stronger geomagnetic effects should produce stronger couplings. Others have interpreted it as evidence against the hypothesis, on the grounds that the correlation is simply tracking the storm frequency, not a causal mechanism. Both interpretations are internally consistent. The data hasn't yet decided between them. The solar cycle interaction adds another layer. Within any given solar cycle, there are phases of high activity and phases of low activity. Equinox enhancement applies on top of whatever phase we're in. Right now, we're in a relatively active phase, near the peak of the current cycle, combined with equinox alignment. The geomagnetic system is, on average, more responsive right now than it is at most other times, which again means that the prior probability of observing any given overlap between storms and earthquakes is elevated during this window. The math is doing extra work in our favour. We have to account for it before we can conclude that anything unusual is actually happening. This is why researchers focus on equinox windows, even though, paradoxically, equinox windows are also the periods with the highest risk of false positives. The logic is that if a real effect exists, it should be easier to see when the coupling is strongest. The risk is that apparent effects during equinox windows are artifacts of the enhancement, rather than evidence of the underlying mechanism. Separating the two is hard, and this difficulty is one more reason why the central thread, whether tonight's clustering is signal or noise, is so resistant to a clean answer. We're looking in exactly the right place if something exists. We're also looking in exactly the wrong place if nothing exists, but we want to see something. The catalogue problem. There is another deeper source of uncertainty in this whole conversation, and it has to do with the earthquake catalogue itself. We treat global earthquake records as if they are a complete and objective measurement of what the Earth is actually doing. They are not. They are the product of a global network of seismometers, analysis algorithms, and human judgment, all of which have biases and limitations that shape what ends up in the catalogue. Earthquake detection depends on sensor density. Regions with dense seismometer networks like Japan, California, Italy, and New Zealand detect smaller earthquakes and produce more precise locations and magnitudes than regions with sparse networks. The deep oceans, large parts of Africa, Central Asia, and polar regions have much less dense coverage. Earthquakes in those regions are detected primarily by distant stations, which gives less precise parameters. Small earthquakes in remote regions may not be detected at all. This creates a structural bias. If you're studying global earthquake statistics, the catalogue you're working from is systematically incomplete for certain regions and certain magnitude ranges. The magnitude of the bias depends on the time period you're looking at. Modern catalogues, from roughly 1960 forward, are much more complete than historical ones. But even modern catalogues have gaps. Magnitude estimation itself has uncertainties. The initial magnitude reported for an earthquake is often revised over the following hours and days as more data comes in from distant stations, and more sophisticated analysis is applied. An event initially reported as magnitude 5.8 might end up at 5.5 or 6.1 in the final catalogue. These revisions are normal and scientifically honest, but they create a moving target for real-time analysis. The clustering we're discussing tonight is based on initial or near-initial magnitudes. By tomorrow, the three events might be slightly rescaled. It's unlikely to change the story qualitatively, but it's worth knowing. Reporting delays are another factor. Not every agency updates its catalogue at the same speed. The USGS, the European Mediterranean Seismological Centre, the Japan Meteorological Agency, and various other regional agencies all maintain their own catalogues with their own update cadences. Events in remote regions may take hours to appear in the global catalogue after they occur. Real-time analysis is always incomplete for the most recent hours, which is precisely the window we are most interested in for a study like this. Historical dataset inconsistencies make long-term studies harder. The definitions of magnitude have changed over time. The methods of locating earthquakes have improved. The stations contributing to global networks have expanded and contracted. Comparing earthquake rates from 1960 to 2026 is not as straightforward as comparing equal measurements taken with the same instrument. It requires adjustments for catalogue completeness, which introduces yet another source of uncertainty. The impact on correlation research is significant. If you're looking for a weak correlation between solar activity and earthquake rates, and your earthquake data has structural biases that vary in time and space, you can easily generate apparent correlations that are actually artifacts of the catalogue rather than features of the Earth. You can also miss real correlations because the catalogue doesn't resolve the relevant events with enough precision. Serious researchers are aware of these issues and try to control for them. But no control is perfect. Every solar seismic correlation study is to some extent limited by the catalogue underneath it, and every apparent signal in the data has to be interpreted with the catalogue's limitations in mind. The central thread, whether today's clustering means anything, is inevitably entangled with the question of whether the catalogue is accurately representing what the Earth did today. On this front, the short answer is probably mostly yes, but with error bars we can't fully quantify, which means our conclusion has error bars too, and error bars in a topic with effects as weak as the one we're investigating can swallow the signal whole. The clustering illusion. I want to bring in some context about what else has been happening in the last few days, because it helps illustrate how the perception of clustering extends beyond just solar and seismic events into the entire media environment surrounding them. In the past few weeks, we have had two near-Earth asteroid passes by objects designated 2026 HQ and 2026 HJ. Neither posed any actual threat. Both were in the routine range of near-Earth object monitoring, but both got coverage because coverage generates clicks. There have also been nearly 500 active weather alerts across the United States for various storms, flood warnings, and severe weather advisories. Each alert is individually mundane. The total number is elevated but not unprecedented. Now combine all of this. A solar storm with the NOAA alert, 3 magnitude 5 plus earthquakes, 2 recent asteroid passes, nearly 500 weather alerts. Depending on which newsfeed you follow, you might get a strong impression that the world is coming apart at the seams, that multiple unrelated systems are all going off at once, and that there must be some underlying reason tying them together. There isn't. Each of these phenomena has its own independent causes. Solar activity is driven by the sun's internal dynamo and its 11-year cycle. Earthquakes are driven by tectonic stress release. Asteroid passes are orbital mechanics. Weather alerts are driven by atmospheric dynamics. The causal structures are entirely separate. What they share is our attention. This is the cognitive load stacking effect. When you're paying attention to one unusual event, your threshold for noticing other unusual events goes down. You become more alert to disruptions in general. The availability heuristic, which is the mental shortcut by which we judge the frequency of events based on how easily we can recall examples, kicks in hard. If you can easily recall the storm, the quakes, the asteroids, and the weather alerts, you judge disruptive events as more frequent than they actually are. The world feels more unstable, than the base rates would suggest. Media amplification accelerates this. Every alert produces coverage. Coverage produces social media discussion. Discussion produces more coverage. The perception of global simultaneity, the feeling that everything is happening at once, emerges from this feedback loop rather than from the actual rates of the underlying events. A given week with a storm, 3 M5s, 2 asteroid flybys, and 500 weather alerts might be entirely within normal variance when you tally the base rates, but it feels extraordinary because it's all visible simultaneously in your feed. Narrative compression is the final layer. Human beings think in stories. We want causes and effects, beginnings and endings, protagonists and antagonists. When multiple things happen at once, our brains compress them into a single narrative, even when the underlying events are causally disconnected. The narrative becomes the cluster becomes the story, and the story, once established, becomes much harder to dislodge than any single piece of evidence within it. This is why unrelated systems feel connected even when they aren't. And this is why we have to keep returning to the central thread, because the central thread is the only thing that forces us to disentangle the story from the evidence. The solar storm and the 3 earthquakes are the specific question. Everything else, the asteroids, the weather alerts, the general sense of unease, is noise around that question. It is context, not content. And mixing context with content is how careful thinking turns into pattern finding that goes nowhere. The 3 interpretations. Let me organise the full landscape of how we can think about what we're seeing tonight, because there are really only 3 distinct interpretations available, and each of them has strengths and weaknesses worth laying out directly. The first interpretation is coincidence. This is the default scientific model. It says that the 3 earthquakes tonight are independent events, unrelated to the solar storm, unrelated to each other, and unrelated to any global process tying them together. The clustering is within the expected statistical variance for a random process, with the baseline global M, 5+, rate of 1 to 2 events per day. Yesterday's null result supports this interpretation. The energy physics supports it. The lack of a consistent mechanism across proposed coupling hypotheses supports it. Occam's razor supports it. This interpretation requires no new physics, no new mechanisms, no revisions to existing theory. It fits the data as we know it. Its weakness is that it is, in a sense, boring. It doesn't satisfy the narrative instinct. It treats the striking overlap we're observing as a quirk of randomness, which is emotionally unsatisfying even when it is intellectually correct. It also has the unfalsifiable quality that any null hypothesis can take, which is that it leaves the door open for future evidence without making specific predictions about when that evidence should arrive. The second interpretation is the weak signal hypothesis. This says that there is some real but small coupling between solar activity and earthquake timing, mediated by one or more of the mechanisms we've discussed: geoelectric currents, piezoelectric effects, fluid electrokinetics, or some combination. The signal is real but small enough that it disappears into the noise on most days, and it is visible only when several enhancing factors align, such as an active storm during an equinox window with faults near their failure threshold in regions with favourable conductivity structures. Tonight's clustering might be consistent with this interpretation if the 3 faults involved were sitting at their failure thresholds, and the storm's local effects at each site were sufficient to nudge them into breaking. Yesterday's null result is not incompatible with this interpretation, because yesterday may not have had faults at failure thresholds aligned with enhanced storm conditions. The weakness of this interpretation is that it is nearly unfalsifiable. The signal is always postulated to be just below the noise floor. Any evidence can be accommodated. Any non-evidence can be explained by the signal's weakness. It survives not by making bold predictions, but by making modest ones that are hard to test. The third interpretation is the wrong variable framework. This says that we are looking at the wrong correlations because we are using the wrong indices. Maybe KP is not the right metric. Maybe we should be looking at decibels by dt spikes at specific latitudes, at particular ionospheric current configurations, at combinations of solar wind speed and magnetic field orientation that don't map cleanly onto any standard index. Under this interpretation, the solar earthquake connection might be real, but it might also be invisible to most studies because those studies are tracking the wrong physical quantity. Tonight's clustering might reflect a particular configuration of the relevant variables, which isn't captured in the simple G2 label we've assigned to the storm. The weakness here is that this interpretation requires us to essentially start from scratch in terms of analytical methodology. It says that decades of studies using standard indices might all be uninformative, which is a strong claim. It also leaves us without a clear path forward, because if we don't know what the right variable is, we don't know how to look for it. None of these three interpretations has definitive evidence supporting it over the others. None of them can be definitively refuted either. The honest position, and I want to be very clear about this, is that we are operating in a space of genuine scientific uncertainty, where multiple reasonable interpretations can accommodate the same data, and the data is not yet rich enough to decide between them. This is uncomfortable, I know. We want answers. We want to know what's happening and why. We want certainty, and when we can't have certainty, we want at least a best guess that we can commit to. Science, at its best, doesn't give us those things when the evidence isn't there. It gives us a map of the uncertainty and tells us where the boundaries are. Tonight we have 3 earthquakes, a solar storm, a compelling visual overlap, a century of conflicting studies, several proposed mechanisms with varying degrees of plausibility, and no resolution. The central thread survives in the gap between interpretations. It survives because none of the 3 can be ruled out. It survives because humans, collectively, need the question more than they need the answer, and that is, I think, the most important thing to sit with. The reason this question refuses to disappear is not that the evidence keeps piling up on one side. It's that the evidence keeps arriving in small, ambiguous amounts on multiple sides, and none of them is yet decisive. It's not a cover-up. Before we get to the deeper reasons this question keeps surviving, I need to address something directly, because it comes up every single time I cover these topics, and ignoring it would be dishonest. Some people watching this will immediately think of HAARP, the High Frequency Active Auroral Research Program, the facility in Alaska that, depending on which corner of the internet you visit, is either a modest scientific research station studying the ionosphere, or a secret weapon capable of triggering earthquakes, controlling weather, and doing about a dozen other things that would violate several laws of physics. Let me be clear and neutral. HAARP is a real facility. It was originally funded by the US military and is now operated by the University of Alaska Fairbanks for scientific research. Its purpose is to study the ionosphere using high-frequency radio transmissions to heat specific regions of the upper atmosphere and observe how they respond. It is an instrument for understanding ionospheric physics. It is not a secret weapon. The power levels involved, while impressive for a radio transmitter, are utterly trivial compared to the energy scales of weather systems, let alone earthquakes. The scale mismatch is the same one we encountered with solar storms earlier, only worse because HAARP's output is tiny compared to even a modest solar storm. The claim that HAARP can trigger earthquakes has no physical basis. The power it puts into the ionosphere is roughly comparable to what the sun does naturally, and the sun, as we've established, cannot directly cause earthquakes under any mechanism we understand. HAARP's influence is even smaller and more localized. The idea that it could reach across the planet to destabilize faults in the Kermadec Trench, or the Aleutians or the Carlsberg Ridge, fails on every energy argument you can run. This doesn't mean curiosity about HAARP is illegitimate. Curiosity is fine. Asking what a facility does is reasonable, but treating HAARP as a shadow explanation for every geophysical anomaly is a category error. It confuses scale, and it conflates curiosity with conspiracy in a way that short-circuits actual inquiry. What matters here for the central thread is that there is no hidden explanation being suppressed. The data from the solar storm is publicly available. The data from the earthquakes is publicly available. The analysis tools are open source or freely accessible. The question of whether solar activity can influence earthquake timing is open in the literature, actively discussed, and not hidden by anyone. It is, however, unresolved. And unresolved questions in science are not the same as suppressed answers. They are honest admissions that we don't yet know. I make a point of addressing conspiracy framings directly because I think the curiosity that leads people to them is genuine and worth honouring. People look at HAARP and ask questions because they want explanations for things that don't quite fit. That impulse is healthy. What's not healthy is letting the impulse pull you into frameworks that require ignoring basic physics to sustain. The honest answer to the question of why 3 earthquakes lined up tonight with a solar storm isn't that some secret facility engineered it. It's that we don't have a complete model of how, if at all, the two systems interact, and that our understanding is limited by the tools and theories we currently have. Instrumentation is transparent. NOAA data is published in real time. USGS earthquake data is published in real time. Magnetometer data from global networks is accessible. Whatever the answer to the central question turns out to be, it will be discovered in the open by people working with public data, not in a shadow facility, not behind locked doors. Which brings us to why the scientists who actually care about this question don't talk about it publicly, and that's a story worth telling plainly. Why scientists don't talk about this publicly? There is a real reason why the researchers who study solar earthquake connections keep their interest quiet, and it has nothing to do with conspiracies. It has to do with how academic careers work, and it's worth understanding. Academic careers are built on publishing papers, getting citations, earning grants, and building a reputation in a defined field. Nothing in that structure rewards a researcher for spending time on weak effect questions with inconclusive results. If you spend 3 years investigating solar seismic coupling, and your conclusion is that the effect, if it exists, is too small to confidently detect in current datasets, you have not produced a career-advancing paper. You have produced a paper that confirms the status quo. The status quo is that we don't know. Adding one more paper saying we don't know is not how you get tenure. On the other hand, if you make a bold claim of solar seismic coupling and the claim turns out to be wrong, your reputation takes a hit that is hard to recover from. Fringe-adjacent claims attract skepticism, and rightly so. A researcher who publishes an overstated correlation paper that gets dismantled in the peer review process, or worse, in the months after publication, can find their credibility damaged for years. The reputational downside is asymmetric with the upside. The result is that most researchers who are genuinely curious about the question approach it cautiously. They might run exploratory analyses on the side of their main work. They might mention the question in conversation with trusted colleagues. They might pull up the overlay chart when a striking event like tonight's occurs and think about it quietly and file the thought away. They don't publish papers claiming correlation. They don't promote the hypothesis publicly. They treat it as a private curiosity rather than a research program. This is not dishonest, it's rational. The weak effect science problem is well known across all of science. Topics where the expected effect size is small, and the required sample sizes are large, and the competing explanations are many, are systematically under-investigated. Not because the questions aren't interesting, but because the risk-reward for individual researchers is poor. The field as a whole might benefit from resolving the question, but no single researcher has a strong incentive to take on the resolution personally. Publication bias compounds this. The papers that do get published tend to be the ones reporting positive findings, because positive findings are more interesting to editors and reviewers. The null results tend to stay in file drawers. This creates a misleading picture in the published literature, where the apparent weight of evidence seems to favour the hypothesis more than the full body of evidence, including unpublished studies, actually does. The problem is well documented in many fields and is not unique to solar seismic coupling. There's also the funding and attention constraint. Research funding goes disproportionately to topics with clear applications, clear mechanisms, and clear timelines. Solar seismic coupling has none of those. It's not clear what you would do with a confirmed weak correlation if you had one. It doesn't lead to obvious predictive tools because the effect, if it exists, is too weak to be useful in earthquake forecasting. So funding agencies don't prioritise it. Without funding, dedicated research programs don't form. Without dedicated research programs, the question stays stuck in the margin. Historical parallels exist in geophysics. Plate tectonics itself was a fringe idea for decades before it became mainstream. Continental drift was openly ridiculed by many geologists well into the 20th century. The reason plate tectonics eventually won was that the evidence became overwhelming through seafloor mapping, paleomagnetism, and the development of better theoretical models. If the solar seismic coupling question is ever going to be resolved, it will probably require similar developments, better measurements, better theoretical frameworks, better data coverage. None of those are likely to emerge from individual researchers quietly looking at overlay charts. They would require institutional commitment that doesn't currently exist. So when I said at the start that 3 quiet scientists pull up the same chart every time a storm like this hits, I wasn't describing a secret society. I was describing the normal behaviour of curious researchers who have made the rational career calculation not to publicly commit to an unresolved question. They are doing their real work, and in their spare time they are tracking a private curiosity. The central thread continues because they keep looking. It doesn't resolve because none of them, individually, has the resources or the incentive to resolve it. The real reason the question survives. Here is what I think is the deepest reason the question keeps coming back. Year after year, storm after storm, cluster after cluster. It's not that the evidence keeps accumulating. It's not that scientists are suppressing an answer. It's that the nature of the evidence we have is structurally ambiguous in a way that almost guarantees the question will never be cleanly resolved by the methods we currently have. Weak signals in complex systems are extremely hard to pin down. When the expected effect size is small, when the noise from other sources is large, and when the underlying mechanisms are poorly understood, statistical analysis can produce apparent signals that are artifacts and can miss real signals that are buried. The tools of statistics are designed for situations where the signal is reasonably strong compared to the noise. In situations where they're comparable, statistics gives ambiguous answers. The solar seismic coupling question has been studied for decades. The body of work includes papers that find correlations, papers that find nothing, papers that find correlations in subsets of data, papers that find different correlations with different methods, and papers that point out methodological problems with the earlier papers. Across the full body, there is no clear resolution. The weight of evidence tilts slightly toward the null hypothesis, but not decisively. The weak positive findings are enough to keep the conversation going. The strong null findings are enough to keep it from becoming mainstream. The stalemate has been stable for a long time. Human pattern sensitivity is part of the reason the question keeps returning. We're biologically wired to notice coincidences. When 3 earthquakes cluster during a solar storm, we notice. When 3 earthquakes cluster on a quiet geomagnetic day, we don't pay attention. The asymmetry in our attention ensures that the cases that seem to support the hypothesis are the ones we see, while the cases that refute it fade into the background unremarked. This isn't a conscious bias. It's a fundamental feature of how perception works in a brain shaped by evolutionary pressures to find patterns in uncertain environments. Scientific incompleteness in our understanding of Earth systems is another factor. The Earth is a coupled system. Its atmosphere, oceans, magnetosphere, ionosphere, and solid Earth all interact in ways that we are still working out. The idea that every known coupling is already catalogued and that no weak couplings remain to be discovered is not supported by the history of geophysics. Every few decades, a new coupling or influence gets mapped. Sometimes those couplings are significant. Sometimes they turn out to be marginal. But the space of possible couplings is not yet fully explored, and treating it as closed is premature. Noise never fully resolves. In any complex system with multiple interacting processes, there will always be residual variance that cannot be attributed to known sources. Some of that residual variance might be due to unknown mechanisms. Most of it is probably due to the random nature of complex systems. Without the ability to partition the residual variance into known and unknown contributions, we can't say whether the unexplained fraction is evidence of something interesting or just the irreducible randomness of the universe. New measurement technology might eventually change this. If we ever build a dense global network of high-resolution magnetometers, coupled with improved fault zone monitoring, coupled with better theoretical models of critical state fault behavior, we might finally have the tools to answer the question. Satellite missions dedicated to measuring solar wind, ionospheric response, and ground effects with high spatial and temporal resolution could transform the data. Improved understanding of fault zone hydrology could allow us to model the near-failure state of specific faults in real time. None of this exists yet at the scale needed to settle the question, but it's conceivable. Future possibility space remains open. The history of science suggests that hypotheses that persist at the edge of mainstream acceptance, without being either confirmed or definitively refuted, sometimes eventually get resolved in surprising ways. They might be confirmed by new evidence. They might be refuted by better theoretical understanding. They might turn out to be partially right and partially wrong, with the truth being more complex than either side originally proposed. Solar seismic coupling could go any of these ways. The question is not closed. It's open, specifically because the evidence is limited and the field hasn't committed to resolving it. Why closure has not been achieved is the simplest way to state the situation. Nobody has produced evidence strong enough to confirm the hypothesis. Nobody has produced analysis comprehensive enough to rule it out. Nobody has proposed a mechanism specific enough to be definitively tested. Until one of those three things happens, the question stays open. And in the meantime, every time a day like today arrives, the question re-emerges. Not because the evidence is accumulating, because the evidence is inconclusive, and inconclusive evidence is the fuel that keeps questions alive across generations. Today versus yesterday. Let me come back to the thing that, for me, is the most quietly unsettling fact about this whole story, and it's the two-day contrast. Yesterday and today, the solar conditions were similar. Yesterday showed no clustering, today shows clustering. Over 24 hours, the picture flipped, and nothing about the sun changed meaningfully. This is the replication problem in its sharpest form. If the correlation were real and strong, we would expect more consistent results across similar conditions. The fact that we get opposing signals from consecutive days with comparable solar inputs is exactly the pattern we'd expect from a null hypothesis, where any apparent correlation is an artifact of the natural variance in earthquake timing. Yesterday's low variance day and today's high variance day together average out to the baseline rate. Neither is surprising. Together they tell us that the variance band is wide and the mean is normal. This instability of short-term inference is a recurring theme in real-time analysis of natural phenomena. You can convince yourself of almost anything by looking at a few days of data. You need weeks, months, or years of data, consistently analysed with the same methodology, to extract signals that are more than noise. 1 day doesn't tell you much. 3 days tells you a little more. 1,000 days tells you something reliable. We are constantly in the position of looking at 1 day and trying to infer the whole pattern, and it almost never works. The importance of long-time series analysis can't be overstated here. If we want to know whether solar storms correlate with earthquake rates, we need to look at years of both datasets, matched at the right time resolution, with proper statistical controls for seasonal variation, solar cycle phase, catalogue completeness, and methodological choices. Nobody has done this perfectly. The studies that have been done are each limited in one way or another, and they have produced conflicting conclusions. Until a rigorous long-term study is done, preferably pre-registered and conducted by multiple independent groups, we won't have a definitive answer. Snapshot interpretation is misleading. What we're doing tonight, looking at 1 storm and 3 earthquakes and asking whether they're connected, is exactly the kind of snapshot analysis that science tells us not to trust. Not because snapshots are uninteresting, but because snapshots can't distinguish signal from noise. Any single snapshot can tell any story you want to tell, depending on how you frame it. The frame matters more than the snapshot when the underlying signal is weak. Scientific requirement for reproducibility is the backbone of all of this. A finding that appears in one study and cannot be reproduced in subsequent studies is not a confirmed finding. It's a tentative observation that needs further investigation. Solar seismic coupling is in that state. Some studies find it, others don't. Reproducibility, in the strong sense of multiple independent groups finding the same result with independent data and methods, has not been established. Until it is, conclusions are tentative by necessity. Why conclusions must remain tentative is the plain answer. We don't have enough data, with enough consistency, analysed with enough rigour, to commit to a definitive statement about whether solar storms affect earthquake timing. We have suggestive patterns that come and go. We have mechanisms that might plausibly explain small effects without any of them being confirmed. We have statistical analyses that produce different conclusions depending on methodological choices, and we have the central thread, which is the observation that on some days, like today, the overlap is striking, and on other days, like yesterday, it isn't. The thread doesn't give us the answer. It gives us the question, over and over, refusing to go away. Tonight's clustering does not prove causation. Yesterday's null result does not prove the absence of causation. Both together give us a data point in an ongoing investigation that has lasted decades and will likely last decades more. The investigation is not closed, the answer is not known, and the honest position is to say that, and to keep paying attention, and to update our beliefs carefully as new data comes in. The unanswered question. Let me restate all of this cleanly one more time, because I want to make sure that when you walk away from this video, you walk away with the raw facts rather than the narrative I've been layering on them. Right now, a G2 geomagnetic storm is active on Earth. It is driven by a coronal hole high-speed stream from the Sun. The KP index reached 6. NOAA issued an alert. This is a real event, moderate in intensity, well within the normal range of space weather activity for the current phase of the solar cycle. Within a 7-hour window during this storm, 3 earthquakes occurred at magnitude 5 or greater on 3 tectonically unrelated fault systems, a magnitude 5.9 in the Kermadec Trench, a magnitude 5.5 on the Carlsberg Ridge, a magnitude 5.0 in the Aleutians. These are the facts. They are verified, they are public, they are measurable. The 3 fault systems involved are independent. They have different stress regimes, different depths, different mechanical properties, and no known physical coupling between them. Seismic waves from one cannot trigger earthquakes on the others at the magnitudes involved. They are, as far as current geophysics knows, sovereign events. The global baseline for magnitude 5 plus earthquakes is roughly 1 to 2 per day. 3 events in 7 hours is elevated but not statistically unusual. Clusters of this size are expected multiple times per year from random variants alone. The clustering observed tonight is consistent with a purely random distribution. Yesterday, under similar solar conditions, no clustering occurred. The 2-day contrast is itself a data point in the larger question. Any causal story would have to account for why the storm correlated with clustering on one day and not the other. No simple story does. The energy physics of the situation makes direct causation, where the storm supplies the energy to break a fault, extremely implausible. The storm's energy is delivered to the wrong location in the wrong form at the wrong scale. There is no known mechanism by which direct causation could work. Indirect triggering, where the storm supplies a small perturbation to a fault already at its failure threshold, remains theoretically possible but untested. We cannot currently measure which faults are at failure thresholds with enough precision to design a rigorous test. Multiple mechanisms have been proposed, including geoelectric currents, piezoelectric effects in quartz-bearing rocks, and electrokinetic effects in fault-zone fluids. None has been confirmed, none has been definitively refuted. They sit in various stages of theoretical development. Statistical studies of solar seismic correlations have produced mixed results. Some studies find weak positive correlations in certain datasets. Other studies find nothing. The dataset sensitivity of the results suggests that real signal, if any, is small compared to methodological noise. Replication across independent studies has not been achieved. The question of solar earthquake coupling is not suppressed. It is unresolved. It remains open in the literature, discussed quietly by researchers who find the question interesting but unresolvable with current tools. It is not a conspiracy. It is a weak effect scientific problem. And the hidden something in tonight's storm, the thing the title of this piece referred to, is not a hidden earthquake or a hidden mechanism or a hidden conspiracy. It is uncertainty itself. The hidden something is the epistemic gap we still have in our understanding of how, if at all, 2 distant and seemingly unconnected parts of Earth's system might influence each other in subtle ways. That gap is real, it is meaningful, and it is why the question refuses to die. Future research directions would include dense global magnetometer networks with high time resolution, real-time fault stress monitoring on major subduction zones, pre-registered long-term statistical studies of solar seismic correlations using multiple independent datasets, and theoretical work on non-linear triggering processes in near-critical systems. None of this is happening at scale today. Some of it might happen in coming decades. Until it does, the question will stay where it is, alive and undecided. The philosophical tension at the heart of all of this is between coincidence and unknown coupling. 2 possibilities, both consistent with current evidence, one boring and parsimonious, the other interesting and speculative. Science at its best treats boring as the default and requires interesting to earn its keep with evidence. Interesting has not yet earned its keep on this particular question. But it hasn't been sent home either. It's still in the room, sitting quietly in the corner, waiting for the next storm to arrive. Tonight, a storm arrived. 3 earthquakes happened. The question resurfaced. Tomorrow the storm will fade, the earthquake rate will return to its baseline, attention will move on to something else. and the question will sink back below the waterline where it has been living for decades. It won't disappear, it will be waiting for the next storm, and the storm after that, and the storm after that. Because the evidence is weak, the mechanisms are plausible but unproven, the data is inconclusive, and the science is legitimately unresolved. Closing. Let me bring you back to where we started, because I think it's worth one more look at the timeline with the narrative stripped away. A G2 geomagnetic storm is active. The KP index reached 6. NOAA issued an ALTK06 alert. Within a 7-hour window during the storm, 3 earthquakes occurred at magnitude 5 or greater on 3 different fault systems: a magnitude 5.9 in the Kermadec Trench, a magnitude 5.5 on the Carlsberg Ridge, a magnitude 5.0 in the Aleutians. That is the entire set of events. Those are the facts. Everything else I've said tonight has been layered interpretation, proposed mechanisms, statistical context, and discussion of what the data might or might not mean. The underlying events, stripped of interpretation, are these 4 items and nothing more. The storm is real, the earthquakes are real, the timing is real, but the connection between them, if any, remains unproven. No physical mechanism has been confirmed to link solar activity to earthquake timing. No statistical study has produced unambiguous evidence of causation. No experiment has successfully triggered a seismic event using solar-scale electromagnetic perturbations. The correlation, if it exists at all, is weak, inconsistent, and hidden in the noise of 2 complex systems that are largely independent of each other. The 3 quiet scientists who keep checking the overlay chart every time a storm like this hits are not seeing something the rest of us are missing. They're seeing the same thing we're seeing. A striking temporal pattern that might be signal, or might be noise, and that refuses to declare itself one way or the other. They keep looking because they find the question interesting. They don't publish what they see because they don't have the evidence to publish anything definitive. They're not hiding truth. They're holding a question open that the rest of their field has, not dismissed but chosen not to prioritize, and that is exactly why this question refuses to disappear. The storm is real, the earthquakes are real, the timing is real, the connection remains unproven, and tomorrow, when the magnetosphere is quiet again and the faults have gone back to their slow accumulation of strain, the question will still be sitting there, in the margins of a field that cannot quite close it, and cannot quite commit to it, waiting for the next KP spike to bring it back to the surface of our attention. It is not a mystery that will be solved by any single video or any single paper or any single storm. It is an open edge in our understanding of how the Earth and the Sun interact, and the honest answer, the one that serious researchers give when you pin them down in private, is that we don't know yet, and we might not know for a long time. Keep watching the sky, keep watching the ground, keep watching the overlap, and if you ever find yourself certain of what it all means, one way or the other, that is probably the moment to go check your certainty against the data, because the data so far has refused to be certain about anything, and that is exactly why this question refuses to disappear.